Yeah, okay, our next speaker is Georgii Potapov, who will be talking about E-Variable-Approximability for class tests.
Hello, so I'll talk about E-variables, but first we'll start with the more well-known object that is testing of randomness. Well, just to remind definitions, and average bounded, we will only consider this one. Test of randomness is just this lower semi-computable function that takes values in the range from 0 to plus infinity and is at most 1 on average whenever its second argument agrees with the probability distribution. And we can always consider a universal uniform test, which is optimal in the meaning that it is asymptotically larger than any other test. Okay, and perhaps even more well-known and well-recognized object is the binary logarithm of the universal uniform test of randomness, which is called randomness deficiency. And in the simplest case, when we have natural first argument, or there's something that's finite binary string, and we have simple uniform, meaning uniform distribution as its second argument, and then it is conveniently expressed as the difference of logarithm of the size of the support and minus conditional prefix Kolmogorov complexity. So what about other cases? They were also studied. So, for example, Georgii actively studied tests of randomness and those randomness deficiencies for any arbitrary constructive metric spaces. And a rather well-known work of Bienvenu and others considers also randomness deficiency and randomness tests for families of probabilistic distributions. That would be, instead of having second parameter which accepts probability distribution, we just assume, we just work with function that would be a randomness test for any distribution from the given family. And in particular, it is known that when the family P calligraphical is effectively compact in the set in the space of all probability distributions, then infimum of randomness deficiency or of universal randomness tests, this infimum exists and is lower semi-computable. But what about cases where the set P is not actually effectively compact and not even closed? For example, we can consider such well-known distributions as Poisson distributions and uniform distribution on initial integer segment. And these families would not be compact. They would not be even topologically closed, so you can easily see it by taking the limit of the parameter to the infinity. However, for this case, it's also possible to find the good expression for randomness efficiency, and the method that is used is based on E-variables. Basically, statisticians looked at tests of randomness and decided that without logarithm probability, it would be a nice subfield of probability theory. So E-variables are just essentially the same thing, but without any requirements on logarithm imputability. And for E-variables, we can see that if you have an E-variable for each parameter, then we can use them to build together E-variable for the corresponding composite hypothesis. So essentially, the only bad thing about this construction is that it has some unknown, unspecified constants, but in algorithmic information theory, this is not a big issue because everything is already defined up to some unspecified constant. And so we can use these properties, E-Variable-Approximability, to show that universal class tests for Poisson distributions and for uniform distributions, they exist, and they have a nice expression in terms of meaning that we can have we can estimate the correct parameter. And so from here, it's not difficult to go further. And if we carefully write it down and I see that many things can be easily approximated one with another, then we can get a rather explicit way to express Poisson's efficiency. And what is nice is that initially Poisson's efficiency assumes all possible parameters, all possible real positive parameters. But here we do not need this this structure of the set of the real numbers. We are basically returning to the old familiar Kolmogorov complexity with integer arguments. And so with these two expressions, it's not difficult then to just subtract one from another and get to more inequalities or equalities that can estimate the difference between how non-random n is if we assume that it comes from some uniform distribution versus how non-random n is when we assume that it comes from some Poisson distribution. And with this additional bounds in mind, it's again not really difficult to see that for infinitely many n, well, basically we will have infinitely many cases of each of the following cases where both these values are 0, attain their minimum, whether they're both maximal, or when one is a minimal, Poisson minimal, it's always should be less than for a uniform distribution. So when the Poisson is 0 and uniform efficiency is maximum possible, considering that Poisson's efficiency is 0. And this is basically preparation for further work. I'm in particular interested in how we can do this, but for continuous distributions, and how can we do this for non-one-dimensional families, maybe for perfectly, even for non-parametric cases. And that's all. Thank you for your attention.